Okay, so we've got the practice exam here. The first question asking about the molar ratio of aluminum to oxide in aluminum oxide. What is that question asking us?
So like the 2 to 1, 1 to 2, what is the balance of it, right?
Yeah, it's basically asking us for what the coefficients are that we have in the empirical formula. Does that make sense? The subscripts. So aluminum to oxide, aluminum would be 2 and oxide would be 3.
So it's always based on the first element going to the right.
Well, it's because of the way that the problem is asked, right? It says aluminum to oxide.
Oh,
Aluminum
okay.
here and oxide here. Does that make sense?
Yep.
Okay, Danica, I have a question.
Yes.
It's the ratio is 2 and 3, right?
Correct.
Okay, and then every question you ask, the molar ratio is gonna be ammonium 2 and oxygen 3, right?
No, there are different ways that I could ask that question. Right here specifically, I'm asking for the ratio of aluminum to oxide, right? But I could be asking for the molar ratio of aluminum in aluminum oxide, right? That's a different problem.
Oh,
Does that make sense?
yeah.
So there's different ways, different permutations of that question that I could ask, but the thrust of the question, what it's trying to ask you is, do you understand the empirical formula? Does that make sense? Everybody all right with me there?
Yep.
Cool. Questions? So the next question is doing something pretty, right? So it's asking you for how many oxygen atoms this molecule would have, right? So how many oxygen atoms would this molecule have?
6.
6. Is everybody comfortable with how we find that?
I am now.
So this 2, right, is multiplied into the 3,
Okay.
the 1 that's implicit here on the P, right? It does not apply to calcium, right? Important. So 2 times 3 gives us 6. So that would be the correct answer here. 3 here. Everybody all right so far?
So if you asked us for how many calciums were in that molecule, it would just be 3, correct?
Correct, exactly, yes. Okay, so the next one, strongest intermolecular force is?
Hydrogen bonds.
Hydrogen bonds, exactly, right? Hydrogen bonds are the strongest.
Why? I don't know
It's,
why.
So that's the definition of intermolecular forces. We have dispersion are the weakest. Everybody has dispersion, but they're the weakest. Dipole-dipole are the next strongest, and hydrogen bonds are the strongest type of dipole-dipole. Everybody cool with that? So if we're ranking strength of intermolecular forces, the strongest is always hydrogen, then dipole-dipole, then dispersion is the weakest.
And Professor, for hydrogen will be only hydrogen bonds will be only hydrogen oxygen with fluorine and nitrogen, right?
Correct. So you can only have hydrogen bonds when you have these particular bonds in a molecule.
Okay.
Sorry for my childlike handwriting. Okay. This is why grading takes me so long, by the way, guys, just so you know, because I literally feel like I'm finger painting on all of your papers while I'm grading. Like I could write this stuff. I could write this stuff on a piece of paper so quickly, but anyways, sorry, tangent. So another important thing to note about hydrogen bonds, right, is it's not just enough to have oxygen or hydrogen in a molecule, right?
Yeah.
They have to be bonded together, right? So just having nitrogen and hydrogen is not enough. You have to have nitrogen bonded to hydrogen, right? Everybody comfortable with that? Cool. Questions? Awesome. So bond between nitrogen and nitrogen will always be
Non-polar.
non-polar, right? So when we define polar versus non-polar bonds, right, we said there are two ways to tell that you have a non-polar bond, right? The easiest way to remember them is by who's non-polar. Everybody else is polar, right? So if you're non-polar, right, you are either bonded to yourself or it's carbon bonded to hydrogen, right? Anybody else would have a polar bond. Questions about that one? We're cool. How about this next one? Polar bonds are characterized by sharing electrons equally.
False.
False.
False, right? Polar bonds are characterized by sharing electrons unequally, right? Meaning that there's more electrons being hogged by one of the atoms in the bond than another. Everybody all right? Questions? Okay, so if an atom in a molecule has more electrons than it had in its valence originally, it will have a negative charge.
True.
True, right? So if an atom in a Lewis structure has an extra electron, right, compared with how many it came with in the valence, then it'll have a negative charge. If it had one less electron than it came with in the valence, what would the charge be?
Positive.
Positive one.
Positive. Mm-hmm.
You comfortable with that?
Yeah.
Cool. Having less charges on question? Okay, cool. Having less charges on a molecule will be more energetically favorable.
True.
True. Less charges is better, right? That's why we minimize the charge on a structure when possible. Still okay, guys? Any questions?
Do you think you could mute everyone who's not, like, you know, not talking right now, please? Just because it's going a little bit, it's like pretty laggy for me.
It's okay. Cool. Better?
Thank you.
It could also be my internet sucking, which I apologize for, guys. There's enough of us in the house and enough devices that it's always a struggle. So, okay. So scrolly. All right. So central atoms from row or period 2 are allowed to exceed the octet rule. True or false?
False.
False, right? What row do we get to exceed the octet rule from?
3.
3 and below, right? So from row 3 and below, we're able to exceed the octet rule. 2 and above, no exceeding, right?
Don't you mean to circle false?
Sorry, my bad. I told you my brain was stupid.
All good.
Thanks for looking out, guys. Keep me honest. Okay. The 2 atoms that are allowed to have less than a full octet.
Boron.
Hydrogen and boron.
Hydrogen and boron.
All hydrogen.
And boron. If you put beryllium there, that would be fine too, but we don't usually talk about beryllium, so. Cool. Okay, polar molecules will have symmetric or asymmetric geometries and polar bonds.
Asymmetric.
Asymmetric, right? So in order to have a polar molecule, you must have polar bonds and you must have asymmetry, right? The geometry doesn't have to be where the asymmetry is, right? Where's the other place that the asymmetry could be?
Lone
bond?
pairs.
Lone pairs are asymmetric geometries.
Like in the bonds, like if it's polar, that makes it symmetric.
So polar bonds are definitely required, but I'm thinking about in asymmetric atoms, right? We either have lone pairs or
You have different
It's called
attached
different,
atoms.
different attached atoms.
different attached atoms, right? Does that make sense, guys? Cool. Questions? The Lewis structure for carbon tetrachloride has blank total valence electrons.
32.
32.
So here we have chlorine, we have chloride, we have 4 of them, right? And each one comes to the table with 7 electrons. So 7 times 4 gives us 28, right? Plus the 4 from carbon gives us 32 electrons. So ugly. Plus. Everybody comfortable with that? If there was a charge on this molecule, let's say there was a negative charge on the molecule, right? What would we do with that charge?
You add it.
We would add an extra electron, right? So if there are charges on a molecule, those are also included in the total valence electrons, right? Always. Cool? Excellent. The molecule pictured to the right has blank electrons used in bonds.
6.
6.
6 electrons, right? Everybody all right with that? So if we have a triple bond, right, each one of those lines represents 2 electrons. So 2 times 3 gives us 6 electrons, right? Carbon monoxide has 0, 1, or 2 formal charges.
2.
It has 2 formal charges, right?
How do you know that?
Because I can look at the molecule and evaluate it for formal charges by doing my little box orator, right? How many electrons did oxygen come to the table with?
6. 4. 6.
6 electrons. And how many does it have here?
5.
5 electrons. Right? So what's the charge on oxygen?
1.
Plus 1. Right? And what about carbon? Carbon came to the table with
4.
4 electrons. And how many does it have here?
5.
5 electrons.
How are you counting the 5?
1, 2, 3, 4, 5.
Oh, okay.
Yeah, all of the electrons directly around the atom in the box there. So that would give you a -1 charge here for a total of 2 formal charges. So just because a molecule doesn't have a net charge doesn't mean that it won't have formal charges, right? Does that make sense, guys? Let me say that again.
Please.
So carbon dioxide as a molecule is not a polyatomic ion, right? It's a molecule. Doesn't have a net charge, but it does have two formal charges on it. They just happen to sum to 0. Does that make sense?
Yes.
Cool. Questions about that?
Oh, okay, this one is okay.
So if something doesn't sum to 0, that's when it is a net charge.
Correct, which means it's an ion.
Okay.
Mm-hmm.
Which means it has a metal in it.
No, you're thinking of ionic compounds. You can have ions that don't have metals in them, right? Like, for
okay.
example, an anion or any of the polyatomics.
Yeah.
Right?
Okay.
Yeah. So ion means something has a charge. Ionic is usually referring to ionic bonds, which happen to usually be between metals, metal cations, and non-metal anions or polyatomic anions.
Okay.
Cool.
Yeah.
Good questions.
I just want to clear it up. Even though there's a negative and a positive, and those technically count each other out, it's still considered two individual formal charges.
Correct.
Right.
Yes. Mm-hmm. Yeah. Any other questions about that one?
To figure out our charges, we always just draw our little boxes in our little things, and we'll get it. Okay.
Yeah.
Want to make sure I remember correctly.
That is correct.
You have a message in the chat.
The dipole, there is a dipole on that molecule, yes, and the dipole happens to be opposite the formal charges, right? So that dipole being opposite the formal charges actually makes this molecule have pretty much no separation of charges. So that's not one I would ask you about because it's tricky, right? So I'm always going to give you molecules where it's pretty straightforward whether or not you have a dipole, right? This one's kind of weird.
Mm-hmm.
Any other questions? Cool. All right, carbon dioxide has what geometry?
Linear.
Linear.
Here. Right, 2 attached atoms, 0 lone pairs, right? Cool.
Mm-hmm.
And just a reminder, even though these are double bonds, right, we still just count it as 1 attached atom, right? Carbon dioxide is a polar or nonpolar molecule.
Non-polar.
Non-polar.
Polar, why?
Has symmetry.
It is symmetric, exactly, right? So we have a dipole on this side and we have a dipole on this side, but they are equal and opposite directions, so they cancel each other out, right?
Also because the outside elements are the same.
Also that, right? So if there was a different element here besides oxygen, right, then that tug of war would not be equal and opposite. Does that make sense? Thank you for that one, Carlos. Any other questions about that one? We're okay? Cool. I'm going to skip this one because we can do this one on the board. I'm not going to try and do that on here. It's going to look ugly. So we'll get there. Okay, so calculate the molar mass for each of the following molecules. So I can't stress this to you guys enough. Don't Don't. Units.
Like never again forget units.
No.
Ever.
Just don't, okay? Because that's a lot of the time, it's 50% of the question. Like, so I can tell you that easily the number one thing that students lost points on this quiz was for not putting units in. Literally, there were 3 points in the first question and 2 points in the last question. So 5 total points just for putting down the units, right? You
went back. I went back after and was like, "Oh my God, units!"
Yeah. So please, guys, so important, right? For molar masses, what are our units always?
Grams per mole.
Grams per mole, right? This is another one where I see students, for whatever reason, just put the grams and don't put the moles. That is not the units of a molar mass, right? That's the unit of a mass. Does that make sense? So always, 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 for a molar mass, the units are grams per mole. Write that down right now, you know, just put that in there. Can't forget if I put it down now. So here we have sodium has a molar mass of 22.99. Oxygen, you know what, I can do better. Text. Oh, so much better. Plus 15.999 plus hydrogen is 1.008, right? So that gives me
39.997.
39.97.
That's what I got.
So are you able to round it? Like say I got that, but then I rounded it to 40? Will that still be okay? Or does it have to be the exact units you got?
It doesn't have to be exact, but I can tell you that based on my personal laziness, when I go to make the exam keys, I'm usually not going to put in every rounding permutation of this that you could possibly get, right? I'm always going to give the number that our periodic table, this one, gives you, right? So that's, if you get a slightly different answer from using a slightly different periodic table, it's fine. It would still be correct, right? It would just mean I have to go through and hand rate it. So not a big deal, but yeah. Other questions about that one? For okie dokie. All right. So RB is
170.936.
So we have
sorry, already 85.468.
468. And we have 2 carbons. And we have 4 oxygens. What does that give us total?
258.95. Does anyone else want to correct me?
I got the same thing.
I got the same.
Oops. Now that's on the internet forever. Okay. How much cuter that is. There we go. Everybody comfortable with that?
Yeah.
So again, I think the biggest pitfalls in calculating the molar mass are the units, the units, the units, the units, the units. The second biggest would be every once in a while I see people try and multiply these numbers together, and then they get these like crazy huge numbers, which hopefully you guys know at this point would be wrong. The one other mistake that I see students make is if you have something like this aluminum, the aluminum sulfate down here, right? Where you have a 3 outside and then a polyatomic inside, that the 3 would apply to both the oxygen and the sulfur, right? Not the aluminum, just what's in the parentheses, right? So just making sure that you get the right number of atoms if there are parentheses involved, right?
So I'm sorry, can you repeat that? So you said if there's like a 4 and a 3, you just multiply that, right?
So this 3 that's on the outside applies to the 4 on the oxygen, right? So 3 times 4 is 12 oxygens, right?
Mm-hmm.
And it also applies to the sulfur. So you'd, right? So that's the other way that students will have Daisy with the molar mass, right? Cool.
But you could also keep, I'm sorry to interrupt you, but you could also just keep the whole polyatomic together, right? And do like SO4 and then there's 3 of them instead of doing separating.
So Lindsay likes to do the polyatomic molar mass and then multiply it by 3. Totally valid move. Yeah, absolutely.
Thank you for saying that, Lindsay, because I was like, wait, hold on, that's how I've been doing it. And I was just getting confused about like the whole like individual.
There's more than one way to do it, right? But it is still important to understand that the 3 is distributed to both of these, right? Because if you don't know that, then you're going to have a hard time finding the molar ratios. Okay. So yes, thank you for that, Lindsay. What else was I gonna say? I was gonna say a thing.
And does that only apply when there's parentheses?
Yes. So like, for example, in this molecule, there's no parentheses. So you only have the subscripts applied to whoever's right before them, right? This subscript applies to everything that's in the parentheses. Great question, Abdi. Everyone all right with that? Oh, that's what I was going to mention. So the one other thing that I saw people do on the quiz, which you want to try and be careful of, is writing down the wrong chemical formula on your work. So that if you write down the wrong chemical formula on your work, then you're going to calculate a molar mass, but it's not going to be the molar mass of the correct compound, right? So just double, triple check when you're writing things down on your scratch paper. Make sure you didn't accidentally put in an atom that wasn't there. Okay. Other questions about that one? Easy peasy, lemon squeezy? Okay. So balance the following chemical equation. So for balancing problems, we're always going to make our little, what? Text. Al, H, and SO4. Okay. So in a problem like this, whenever we see a polyatomic ion, I'm always going to leave the polyatomic ion together when I'm doing the balancing, right? It just makes life much easier. Unless you see the polyatomic broke down on the other side, it happens sometimes, but it's pretty rare, right? Does that make sense, guys? Mm-hmm. Cool. So just starting off, pretending like there's ones in front of everything, we would have 1 aluminum. We'd have 2 hydrogens and 1 sulfate. Over here we have 2 aluminums. We have 3 sulfates, and we have 2 hydrogens, right? Is everybody comfortable with that? Cool. So what's the first thing we're thinking we want to do to balance this guy?
You want to balance the aluminum, right?
Sure, we can do that, right? So we have 2 aluminum on this side and 1 on this side. So let's put a 2 here, right? Then we can erase this guy.
Didn't you at one point say that you do the ones that are going to come out even numbers first and then work with the odd, or did I reverse that?
You reversed it, but in this case, it's okay. It don't matter.
So,
Yeah.
but on some, you would want to work with that odd number and then go to your even
Yeah,
distribution.
especially like combustion type reactions, that can be a good strategy, is looking for the odd man out. So what next?
Hydrogens.
Hydrogen.
What about the polyatomic?
So we have 3 sulfates over here. So we need 3 sulfates over here, right? So how do we get 3 sulfates with this guy?
Multiply by 3.
We need a 3 out front here, right? Everybody comfortable with that?
Professor, I have a question.
Yeah.
So I started with the polyatomic, but I multiplied the 3 already. So I ended up with 12. I started off with 12, so I just worked my way, like trying to even it out from there.
Where did you get 12 from?
I'm sorry?
Where'd you get 12 from?
The 4 and the 3.
Ah, so you were doing the oxygen then, not the sulfate.
Yeah.
Yeah, so that's what I mean when I say I don't break up the polyatomic ion, right?
Oh.
It makes it much easier to balance when you just keep it as sulfate. Does that make sense?
Mm-hmm.
Cool. So this coefficient, the stoichiometric coefficient, right? That's everybody's least favorite word right now, is going to be applied to this entire molecule, right? Not just the sulfate. So we do have 3 sulfates here, right? But now we also have 3 times 2 gives us 6. Everybody see that? So how do we get 6 hydrogens over here?
Multiply 3.
Multiply the product by 3 of hydrogen.
So we need to multiply this hydrogen by 3, right? And that would give us 6, right? Now we're all balanced. Huzzah, right? Now, on the Canvas version of this question, you're going to be asked to input all of the coefficients, right? And if you don't put a 1 here, you will lose a point, okay? It is not ambiguous. There is 1. In this case, when we're writing it out by hand, we leave the 1 out, but for Canvas problems, you have to put the 1, right? Does that make sense?
Okay. Yeah, question.
I can't differentiate between you knowing that it's 1 and just leaving it blank. Does that make sense? Like that's not something that I can't magically know that, right? So you gotta put in a coefficient for everybody in the reaction. Does that make sense, guys?
Yes,
Yeah,
I
I
think I
have
accidentally messed up in the lab because I put the whole equation because I didn't change. So I just put the whole equation instead of just putting the 1 coefficient.
Okay. So, okay. You guys want me, for the balancing, didn't I make there be 2 attempts for that one?
Really? 2? Because mine just muted.
Let me, I'll check. I'll make it another attempt. I don't care. If you guys want to go through and do a balancing again, that's fine. Yeah, I haven't graded them yet, so. Haven't I?
No.
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 You guys, I have no idea where I am right now. Can you tell? It's been a long week. Cool. So yeah, I'll do that because that'll help you practice anyways. So
I like being able to like see what I did wrong and reattempt it on those. It helps up here.
I think it's more productive that way. I agree. So cool. I will do that after we're done here. Any other questions about how the balancing this guy goes? Right. So, in the following chemical reaction, circle the reactants.
The methane and the 2 oxygen. 2O2.
So reactants are always on the left side, right? Products are always on the right. Cool. Everybody comfortable with that? Cool. And what type of reaction is this?
Combustion.
Combustion. What about this reaction? What kind of reaction is that?
Composition.
That is a decomposition, right? So whenever you have one thing and it's breaking up into 2 things, that's a decomposition, right? If we had this written the other way around, where we were going these guys to this guy, what kind of reaction would that be?
Combination.
A combination, right? So combination and decomposition are just opposites of each other. Everybody comfortable with those? Cool. We'll save this one for doing on the board because it'll be easier that way. If a sodium metal loses 1 electron to become Na plus cation, it has been
Oxidized?
Oxidation is loss, reduction is gain. Yes. So if we lose an electron, we're oxidized. If we gain an electron, we are reduced. Everybody cool with that? Cool. If an atom goes from an oxidation number of 0 to -2, it has been reduced, right? And again, you can draw out that number line. Anytime you're going to the left, right, you're being reduced. Anytime you're going to the right, you're being oxidized. Brenda, you don't like it. I can't hear you.
Okay, sorry. I was just like picturing the number line in my head, and so if I was going to the negative, that's gain.
Yes.
You were saying? Okay. Yeah, that one just tricks me out. I always have to draw it out because, you know, when you learn it as a kid, you know, negative, you're losing. So you're going, you know. So that's why I always have to draw the arrows. That's why I was making that weird face, like, what way am I going?
You draw a number line in your brain. I get it.
Yeah, it was hard.
That's fine. That's totally fine. So again, on the negative side, right, going from 0 in the middle to your negatives, heading left is always going to get you to reduction, right? Heading towards the positive in the right direction will always get you oxidized. Got it, right? Cool.
I'm all for the pictures, like the molar coasters and the number lines. Like I always draw those at the top of my sheets.
Me too. All right, let me see, do we have, beep, boop, beep. We can answer these guys. So give the empirical formula for C6H12.
CH2.
CH2.
How did you do that?
Because there's 1 6 in the carbon and the hydrogen is 12. So 6 goes in one time and 6 goes into 12 twice.
Exactly. You're looking for the largest common denominator. Am I saying that right? So 6 can go into 6 once, 6 can go into 12 twice, right? Then you end up with 1 and 2, which can't be reduced any further, right? So the empirical formula is always the lowest ratio possible for a compound, right?
So it would always be available that you can just go in and reduce like that? Like if you, on most of them?
It will make a different molecule.
Yeah, but I mean, if we were looking for the empirical formula and
Yes.
it was always like, you know, an 8 and a 4 and stuff like that, we would always just reduce those numbers to the lowest? Okay.
Yeah, but you're
Just
never
making sure.
going to get those higher numbers when you're calculating the empirical formula from the mass percent, because the mass percents by definition are always going to give you the lowest ratio, right?
Okay.
Okay. I'll go through an example of that problem, right? So, other questions about this one? So the empirical formula is always the lowest whole number ratio, right? And then the molecular formula will always be some multiple of the empirical formula, right? So if here our empirical formula is this guy, right?
Mhm.
Which one of these could be a molecular formula for this guy?
Any of them. All of them.
I put C.
I put D.
I put C. Why is it all of them?
Because they're all multiples of.
If I multiply by 2, I get this guy, right?
Oh.
If I multiply by 3, I get this guy, right? If I multiply by 4, I get this guy. Does that make sense, guys? So that's why it's all of the above. Cool. So this is another thing because I honestly hate multiple choice questions, but they are so much easier in terms of setting up problems in Canvas and not having you guys misinterpret what the question is asking, right? Since I can't be there when you guys are taking these. So that makes it really important when you're looking at a problem like this, do not stop at evaluating one of them, right? Like, I'm guessing that each one of you guys picked one of these because jumped out at you. That's the one that you looked at first and you were like, that's right, right? And then you just stopped. So you can't do that with these types of problems, all right? You have to evaluate all of the answers. If you evaluate one and then a second one and that one's not true, right? Then you can eliminate this guy right off the bat, right? But if you evaluate one and then the second one and they're both true, now you're in the running for this last one, right? So you better evaluate the last one. Does that make sense, guys? So there's a certain amount of how to solve multiple choice problems that we just have to know how to do, right? Again, I do not like these problems, but unfortunately they are extremely common in most types of standardized tests. So the best thing we can do is learn how to strategize and approach those problems. So, other questions?
No, but it just clicked.
Good.
I had a quick question on that one. Would it be fair to assume that, like, say this was a totally different problem and carbon obviously didn't have anything, you just took that first 4, that first 2, that first 3. That's why you multiplied them by.
So there's an implicit 1 next to the carbon here and an implicit 1 next to the oxygen, right? So if I imagine I'm multiplying each one of these guys by the same number, right? If that was a 2, then I'd be 2 times 1 here would give me 2, right?
Yeah, okay.
It gives me 6. 2 times 1 gives me 2.
Yeah, I was thinking, like, why did you start, like, automatically? And I was like, oh, because the carbon didn't start with anything and then it has a 4 now. And
Yeah, so if it helps you when you're doing empirical to molecular formulas, go ahead and put in a 1 next to the guys that don't have any. I think it's helpful to get you seeing what you're doing there, right? So, other questions? All right, let's do these nomenclature boys. And what? Nope, I don't here because let's do that on the other format. Okay.
Did she freeze?
I think she froze.
Danica, you're frozen. She's frozen.
Hey.
Oh no. Come back to us, Danica. We were on such a good roll. Oh no, Lisa, you're host now. Okay, she came back.
Sorry,
She's
I want
coming
that
back.
responsibility.